So if the point is moving in the left side of the image of our function, here on the left side, time step 0 to 100, we're moving very quickly. The error is quite large, and then as we slow down, our error decreases and we get a much smoother estimate. And the filter catches up, but the main problem is that there is a latency to the position update. But this we cannot avoid because we are filtering. Which means whatever we do, we are definitely ending up with averaging some values. Even if we use a more complex system like a Kalman filter, we're still calculating a running average. So if things start moving all of a sudden, it takes some time for the system to catch up. Well, let me put that on a separate slide. So what can we do in order to overcome this latency?
We are already we reduce the latency by prediction step, right?
No, the prediction step is not the latency. The problem is right now our prediction step does what, given this particular model? What will be the new position that is calculated by the model? So I have my current state x, right? And then matrix A will tell me how that state x changes to x dash. So given this particular model, where I use two coordinates, x and y, right? X, my state consists of two coordinates, x and y.
Yeah.
Then my prediction would be
DOB x and y.
X and Y, so nothing will change, right? So assume that the point stays in the same position.
Okay, I see.
So that's why that doesn't help us to change our, reduce our latency.
So we need to add in some additional variable to describe the changing, like velocity.
Correct.
And
Yes. And that's exactly what you were investigating in the assignment, right? In the assignment, we were building up more complex models. So the problem is that we assume that the model is constant here. So that we need to change. And the way to do that will be to have a, actually, let me draw it like, let me make it more explicit. Here we have X and Y. Right, so this is what it would look like in our current model, where our A matrix is this matrix here. And H is multiplied by Z. And that gives us a estimated state as well. So let's do that before the update. So Z is our sensor measurement, is mapped to a estimated state, and our state is projected. And this would be our matrix A, this would be our matrix H. So now, how do I change that if I want to model the velocity? Well, that would be in that case, my state would have to change to include the velocity x dot.
Yeah. Right.
And our velocity y dot. And this will be x dot y dot, and then our A matrix will change. Then so here's our updated A matrix. So now my position is not dt0. Right, so this would be our A matrix corresponding to a position velocity model, where I now assume that things are moving at a constant velocity always. So if this is my A matrix, then what would be my H matrix? So the measurement.
There will be identical matrix in the. There will be the identical matrix.
Yeah, except I need to make it a proper state, right? So I need to have 4 coordinates here. And here, or my measurement matrix. Oh, that's why I got we just have to make sure that the matrix multiplications work. So H is actually applied to the state. Yes, that's right. And then that becomes Z in this formulation. So this should be reversed. Here's our measurement. And this is applied to right, so here we get a measurement, so we measure X and Y. In this case, what we actually measure is just the position. So we need to extract the position out of our state. And the state would be here. Right, so on the right hand side for the measurement matrix, we have X, Y, x, y, x dot, and y dot, the velocities and the position and the velocities. And from that, we need to extract our measurements. So now what's the shape of the H matrix? This is not a legal matrix multiplication, right? Because if you want to multiply two matrices, then the number of columns of the first matrix. So if I have a 2 by 2 matrix, then this number of columns has to match the number of rows here, right? Because I'm supposed to go y times x dash times y plus 0 times y dash plus. So I'm missing these terms here. So I must have 4 columns. And then this would be the correct one. So my measurement is the x coordinate and the y coordinate, and I return 2 rows there, right? Because I have a 2 by 4 multiplied by a 4 by 1 matrix. So I end up with a 2 by 1 matrix. And the measurement is going to be the x and the y position. Of course, if we had a velocity sensor, then we could include that in the measurement as well. That depends then on what kind of sensors you have in your robot and what you want to model. But most commonly for SLAM, we can measure position, but we can only measure the position. We can only estimate the velocities. We could just change A and H, and our Kalman filter is going to perform exactly the same. I mean, I don't need to change anything in the predict function and the update step, because this implementation here is simply using the matrices, right? I just pass in H, A, P, so on and so forth. So I just need to set up the model in the correct way. But then this code here actually will run unchanged, assuming that these matrices are the correct have the correct dimensions. So let's do that and set up a new system. But in order to do that, I think I just copy this one. Otherwise, the slides, the notebooks are going to get to be too big. Okay, then here's all the matrices that we need, and then we want to write the code. So my A matrix, I said, now should be a 4 by 4 matrix. And let's say dt is equal to 0.1. So we sample at 10 times per second. And we assume that the velocities now are constant, not the positions. Then our matrix Q models the prediction step. So how much variance we have in the motion. And I just set it to 0.25 and let's make it 0.25 for the velocity and 0.5 for the position. Right, so this is our covariance matrix for the state projection. Now H, as we said, is our measurement matrix. So that should be a 2 by 4 matrix now, where we're only extracting the position X and Y. And R is the matrix that is the noise estimate for the matrix here. So, and I also have to change my start position. So we start at 0, 0, and actually let's start at 0, 0. And also at rest, so 0 velocity in X, 0 velocity in Y. And R is now the update of our measurement matrix. So what size does that have to be?
Just 2 by 4.
2 by 4.
Yeah.
2 by 4. Let me double check. We need H is a 2 by 4 matrix. So in order to compute the gain, right? If we look at this equation here, for our common gain, we have H multiplied by P. So P is, or P dash K would be, that's our current covariance estimate for the entire system. So that is a 4 by 4 matrix, right?
Yeah.
So we have a 2 by 4 multiplied by a 4 by 4. So we end up with
2 by 4.
2 by 4. Then we multiply it by H transpose, which is a 4 by 2. So we end up with a
2 by 2.
2 by 2. So R should be,
Oh, yeah, 2 by 2.
Must be a 2 by 2 matrix. And that just corresponds to the estimate of the variance due to the sensor in the X and Y position. All right, so I think that looks correct. So then let's apply our filter. But I want to make it a little bit smaller, so maybe just 200 points for the figure. And let's try and scale it nicely. Okay. So now we can see our measurements. Also, they're based on the position, not on the velocity. So you can see the latency here, right? Like the purple curve, the orange curve here is behind the blue curve. So then we have our predict step and our correction step. X minus P minus X, P, and Q. So we have a problem with the prediction. So P, where did I set P? P should be a 4 by 4. Here. So I need to set our current position. So we start at 0, 10 and at rest, no velocity, and then P is the covariance matrix for our prediction. So now that includes estimates for both velocity and position. So it's a 4x4 matrix. Actually, this one will be up there. Okay, I'll leave it like that. So we will have now x mark k dot h dot z. I need to generate the measurements. So those will be R is a 2x2. So that's correct. ds. Here, I actually have a bug that should be z minus h dot x minus. So yes, that's the correct formula, and then we can run the Kalman filter now. Now, the interesting thing about this now is that when you look at the prediction matrix and our predictions here, right? That's step 0. So we first print out our current state and then P. So that would be, let me print it nicely. Print P and then and x minus and p minus, but let's just look at x and p. So then what actually happens to our P matrix here? As we step through time. So our position initially, we assumed that we assumed these variances, or actually let me print P first. So we started at 1. Then our initial estimate for X and Y position is pretty low because we ended up with a position that's close to the target location that we started out at. Our velocity estimates are here, and we're starting to also develop some off-diagonal elements, which now means what do these values off the diagonal mean? That's a relationship between X position, right, and the velocity. And it starts to indicate that we're now moving. So if X velocity is high, then there's a correlation to the change in the position. That's what these off-diagonal values here mean. So x and x dot is related, and y dot are related. And similarly, x and x dot, that just gives us the transpose of that. So it should be symmetrical here. And that way we can get our estimate now for the position as it changes. So this here is our certainty about the certain positions that we have. But we can also now estimate our velocities, right? Because in x, I now not only do I have a position estimate, right? But I also have an estimate for the velocity that we're moving at. So we're moving to the right and we're moving down because x, and this is x dot, this is y dot. Okay, I don't know, we got just an announcement here in the apartment block. So the interesting thing about this, or the cool thing about the Kalman filter, is that it allows us to now estimate values of the state that we cannot directly observe. So those are called latent variables as opposed to the observable variables. So now the Kalman filter actually tracks the velocities for us without us actually implementing anything to do this specifically, right? And not only does it track the velocity estimate, but also the uncertainty in the velocity estimate. And then we can just run that model. Okay. Okay, I have to reset my x and y here. So we start at position x is 0, y is 10 at rest, and so no velocity. And my initial estimate for the covariance matrix is just the identity matrix. Now this initial estimate is actually not so important because that's what's going to be updated by the Kalman filter. So now we can see and we can compare the curves. Even if I just run it for 200 here, we're plotting the filtered data, we're plotting the error, and we're plotting an estimate of the covariance here, which is an estimate of just the covariance in X here. So maybe I'll turn that off, then the figures will be bigger. Maybe we don't want to show this one. Two one one, 212. Yeah. And here we're seeing the error decreasing. If you zoom in, you should now see a much smaller latency. Oh, be 2 1 2 1 2 1 2 2 1 1. Did I have this one correct here? It should stay 313. Here's a different location. I will show both of those. Okay, now my scaling is off. So first I want to look at 45 and 20, and then I want to look at 175, 170. And then I want to decay the curve a little bit faster, so I can show it in just 200 points. Actually, let's run it for 1,000. Let's see what that looks like. Oh. And then I don't want 170 here, but 670. Okay, so a little bit hard to see, but this would now reduce the latency of the model. So if the target is moving, now we react faster to it. So the blue line and sort of the error due to the measured filter, due to the filtered data, will be smaller. And what will be the disadvantage? Can you guess? Or you should have seen that in your assignment as well. I have to, because I changed the covariances. If you use the same data and run it on this notebook, where we just have the position model, then here the variance is a little bit too high. The point, the thing that you can observe is that when the point is stationary, we have more noise compared to a position model.
Yeah.
Because if the point actually does stay stationary, due to the noise in the position measurement, we will detect some velocity. If that happens to correlate 2 or 3 times, then all of a sudden our point is going to start moving off, right? The estimate for the point is going to be not stationary because we explicitly put in a velocity of the point, a current velocity of the point. So if your point really is stationary, then a model that assumes that the point is stationary is superior to a model that assumes that the point is moving at constant velocity. So you have to balance those two trade-offs in your model.
But Professor, I have a question.
Mm-hmm.
Yeah. Doesn't the velocity be updated during the position is static? You know, if the point is static, the
Yes,
the
but
velocity should be updated to 0, right?
Yes, but we always have noise due to our measurement, right? So as far as the sensor is concerned, the point is never stationary. Because the sensor will always measure it a little bit above, a little bit below, right?
Yeah.
So because of that, and then we estimate what that variance is in P, right? Our P matrix models what that variance is. And if you always get like one a little bit above, one below, a little bit above, one below, then the filter will still do a very good job. But sometimes they're correlated, so you get like 1, 2, 3 voice noise that are sort of pointing as if it's moving in a straight line. And then the filter is going to say, oh, I know we're moving at a constant velocity. My predictions have been accurate, so I'm predicting the point now to be off to some position. The average of the estimate is going to be correct, but due to the noise in the measurement, you're always going to have a non-zero velocity estimate, and then that's going to move your point.
Okay.
So it will be like this, like more peaks here than if you had just the position model. The position model here would be almost exactly a straight line. But with the velocity, you're now sort of predicting it away from the point, from the true position of the point, and that's emphasized, that's magnified due to taking the velocity of the point into consideration. The same thing happens with just the position model, of course, but because we don't assume any velocity, it sort of drags and it just stays there rather than shooting off in that direction. And of course, you can also have a even more elaborate model, right? You can also model motion under constant acceleration, which is what I asked you to do in the assignment. And then the same sort of effect will happen. Now your stationary point is going to move even more. The estimate of stationary points is going to be more noisy than just a position model. But if your point is moving with the constant velocity, then the estimate is going to be much more accurate for a moving point. And it's one of the sort of laws of robotics that if you want to measure things, then the best thing to measure, the most accurate measurements you can get, would be if you integrate a measurement, if you sum them up, so you calculate the average position or something like that, right? Or in computer vision, if you want to measure the size of a ball or how many pixels are in an object that you detected, that's a very stable measurement, really, because even if the lighting changes, it doesn't change by so much, right? If you just have a single pixel and you need to measure, so for example, if you want to figure out the position of the ball and you use the average of all the pixels that belong to the ball, you get a very stable measurement. If you want to model just the if you want to model the velocity of the ball, that's much harder now, right? Because any difference between the previous and the current position is what you estimate the velocity to be at. That is much more noisy. And if you want to model the acceleration of the ball, that's extremely noisy. So I cannot really recommend that for any kind of robotics application. The measurement is going to be very, very difficult. So dealing with sums, integrals of values in robotics is very nice and stable. Dealing with the velocities of things is much harder to do. You have to be much more careful. Dealing with the changes in the velocity of something is extremely noisy and in practice not really recommended as a rule of thumb. So for example, if I want to model, same thing with computer vision, if you want to model if something approaching you or not, and you take the difference in size, that's going to be pretty noisy if you want to use that in order to determine how far something is away from the ball, from the camera, right? It would be much better to estimate the position of the ball, the distance from the ball to the camera, using the position, which is, and then assuming that the ball is on the ground plane, for example, or having a more elaborate model for the position of the ball. That shouldn't be point, it should be target. Okay, so now our last part for Kalman filters. Or any other question?
Yeah, Professor, I happen to have a question to ask.
Mm-hmm.
Yeah. Let me ask, if you mean the the system is noisy, is more noisy, along with we are adding more safe parameter to track.
No, that's not
just me.
That's not what I meant. Right now, the system is more noisy if your motion model doesn't match. So if you have the velocity model, position velocity model, and your point is stationary, then the velocity sort of adds some extra noise to it, right?
Yeah.
If you just have the position model, then your estimate is going to be less noisy if the point is stationary. But if the point is moving in like the start of the curve where it goes up and down, right? Then your position estimate is going to be much worse because it's going to lag behind the movement of your point. Like you can see the measurements here. Where's the figure? When we zoomed in, there was this latency. I changed it now, so now it's not so clear. But before, it was nice to see the latency of the system. So the blue curve was ahead of the measured, was ahead of the filtered curve. The blue curve was ahead, shifted to the left of the filtered curve. The filter took, because it's filtered, It takes some measurement and then it decides that the point has moved. And so in that case, the position velocity model would be more accurate, because as soon as the point starts moving, we also start estimating its velocity, and we also start moving into that direction. So the latency is going to be reduced. That's the advantage of the position velocity model. For a moving point, the latency is going to be reduced. The effect of your filter on the latency is going to be reduced. But if your point is not moving, then your measurement is more noisy. So depending on what you're tracking, you want to pick a good model that matches that particular domain. So if you're tracking missiles, it's not a good idea to think about them as stationary points, right? Because missiles move very fast at a constant velocity. So you need to track them using position and velocities. And you can do even better, because if you know it's a ballistic missile, you can estimate the trajectory and things like that. But the current velocity of something that moves very fast is very important in order to be able to predict where it's going to be. If you're trying to estimate touch gestures, so where the user touches on a touch screen, then that most of the touch gestures are all clicking on things, right? There's a couple of swipes only. So in that case, it would be better to use just the position estimate. If you're tracking if you're implementing a standard user interface where there's no gestures, and the only thing the user can do is click on buttons, then you could model the position of the button click, right? If you by just taking the position into consideration. So you want to implement a program on Android where the user can paint, and they can paint very fine features. So they can paint basically every pixel. Then your position model would be good, right? Because they're just going to move a little bit to get just the right pixel, and then they want to color it red. If you want to model an application where the user has to use swipe gestures or play a game, and you need to move across the screen, then a position velocity model would be better. Yeah, because touchscreens are also pretty noisy from what I understand. So there's different applications use different kinds of filters in order to provide the best user experience, or the best experience for the user. Okay. Oh, yes. So let's look at extended Kalman filters. Or any other questions before we move on? I will share this one.
But Professor, I have another question.
Mm-hmm.
Yeah, if we use the static Kalman filter model, but
It's not really a Kalman filter model. It's a model of the world, right? The Kalman filter doesn't care. The Kalman filter just takes in matrices and spits out matrices.
Mm-hmm.
So it's the model of the world that that you're trying to represent. But okay, go ahead.
Okay, so what's the advantage of we using Kalman filter to filtering the static point compare with you just take the average of the measure point of the previous the set of points.
Okay, so the advantage is that provably if your points, if the noise is generated using a Gaussian distribution, then the Kalman filter, you can actually prove that it's the optimal filter design. So if you just calculate an average, right?
Yeah.
Then the Kalman filter is superior because it allows you to also estimate the variance. So not only do you get one number, which is the average and the position that you think that you're at, but the Kalman filter also provides you with a number that represents the uncertainty that you have in your position. And it's formally, analytically, the best estimate you can make for those two values. Now, in lots of applications, if your problem is not, if it's only the position, right, and you don't care about the uncertainty estimate, and you don't care, if you don't care about all you care about is the position estimate, and you don't care about the uncertainty, and it's simple enough so that you only need to deal with the actual data, not the estimate of the uncertainty, then you can just use averaging the points, or I like to use exponential averaging, because then I don't need to, you can either have a sliding window of averages that you want to use or an exponential average. That's harder to then just extend into a position velocity model, for example. You need to put in some more thought. If you do all of that, then you actually end up with the same equations as the Kalman filter is using right now. But for many applications, it is actually possible to just use a averaging, especially if you don't care about the uncertainty measurement in your estimate.
Okay.
But actually, one thing that is sort of interesting, which we won't cover in the SLAM course, but nowadays in robotics, from a practical point of view, I think complementary filters are actually very important. So, for example, in humanoid robots, we have IMU in the body of the robot in order to be able to measure the angle and the velocity of the robot, so that we see how it's swaying and if it's leaning over too far to the left or too far to the right, so that the robot can balance. For that, we use a sensor that has a built-in gyroscope and a built-in accelerometer, right? Now, as I said, acceleration is very difficult to deal with in robotics. So we don't actually integrate the acceleration data in order to get position, but we use the accelerometer and the acceleration due to gravity to basically estimate the tilt of the robot, right? So using the accelerometer, we measure the acceleration due to gravity in the direction, then I can measure sort of the angle, the tilt angle of the robot. And the gyroscope measures, with the gyroscope, we can measure angular velocity, right? So we can measure how quick something rotates. And gyroscopes are pretty good. They just have a problem that if you of drift, so if they shift, right, and you rotate 10 degrees left, 10 degrees right, and you go back to 0 degrees, because you need to, in order to get the current angle, you need to integrate the angular velocity readings, right? So if you go left, right, left, right, left, right, and you have this drift error. So this is 0 degrees. Eventually your robot will say this is 0 degrees. That's what you can correct very nicely with the accelerometer. But the interesting thing is that the gyroscope, because it measures angular velocity, if the robot is relatively stable and not moving, not rotating, then the gyroscope is actually quite noisy, right? The accelerometer, if the robot is rotating, the accelerometer is very noisy. But if the robot is sitting still, then the accelerometer is actually very accurate. So complementary filters are filters where certain states you decide to change the behavior of the filter. So for example, if my current estimate of the angular velocity is low, then I determine my position simply by using the accelerometer. And if my current angular estimate of the current angular velocity is high, then I want to use the gyroscope data more. And that's actually in practice, I think, an important feature for lots of robot systems, to be able to combine different sensor measurements. In simple situations, yes, you don't really need the Kalman filter. On the other hand, I already gave you all the code, so it's not that hard to implement. So the basic assumption of the Kalman filter is that motion noise and measurement noise are following a Gaussian distribution. And the justification for that is the central limit theory. Right? So that's one of the assumptions. However, we also have, now we have the, okay, let me cover this one later. At the moment, linear systems that we use are limited to basically straight line movements in the state space, which may be n-dimensional. So, for example, position velocity model, we're talking about linear motions, not just in the position. So the robot is not just traveling in straight lines, but also the velocity is changing constant or moving at a straight line. That's sort of the basic underlying assumption. However, of course, lots of motions are not straight line motions. So what do we do? And this is for the motion, straight line movement, and also the mapping from sensor to state. So our H matrix, this one would be our A matrix. So what do we do if the motions are not straight lines? So, or state cannot be mapped in a straight line, not linearly. So, what would be a kind of model that we cannot represent in a linear, as a linear system? Now, basically anything to do with trigonomics, Trigonometry, yes, that's right. That's what I wanted to say. A simple one, very common one, would be a differential drive robot. Right? So if I have a robot, yeah. I don't know what happened to my space. So if I have a robot like that, yeah, like this. So I have a robot with two wheels that has an orientation. Then what would be the system model for such a robot? So we have X and Y. Right. Then what would be the state of the robot? And what would be my transformation matrix? A. How come? Yeah, I just want to make it a little bit larger. Well, here, if I want to model this robot, then the position X and Y wouldn't be sufficient. Right? So here I would have X, would say the center of the robot as my position. And Y. And now what would be the the point for a differential drive robot is that we have position X and Y, but we also have orientation theta. So in order to model the motion of the robot, how would I do that?
We need to propose a model with a parameter to be determined, and then determine the parameter of our model.
Okay, assume you can use all the parameters you want. But basically the kinematic equations for this robot would be if I want to model it, then the robot sort of can turn, right? Or it can drive in a straight line. So it has angular velocity and linear velocity. And that's what we would have to model, basically. So the model would be x cosine v and y sine of v and the whole point is that you cannot actually implement it as a matrix system. If you try, right, then you'll see that you need to multiply here by the velocity x dot and y dot, the linear velocity that the robot is moving at. So this cannot be represented as a, it's impossible to do that. You can try, but like you just saw when I tried it, this cannot be implemented as a linear system. Basically, that means we cannot convert it into matrix form. Right? Anything that's a linear system, you can represent as a matrix form. And the kinematic equations are very simple, right? But they're still not representable in matrix form. Because we have x is equal to x plus cosine VL, where it's the linear velocity. Sorry, not cosine VL, of course. Cosine theta VL multiplied by cosine theta y is equal to y plus VL multiplied by sine theta. And theta is equal to theta plus the angular velocity. So that should be theta dot. Right? This would be the equations or the kinematic equations for a differential drive robot. And those we cannot represent in in matrix form because we have this dependency here on VL basically. Right? So, and it includes the trigonometric functions, cosine and sine. So this is non-linear. So what do we do? What do we do all the time when we have a linear system and non-linear system, but we have an algorithm that only works for linear systems?
You can
Like
do linear approximation.
Yeah, we're linearizing the system. We're calculating the So we calculate the linear approximation of the system. So in this case, I want to, dot, oh, I don't know, there should be no brackets there. So we calculate the change in our output variables, in this case x, y, and theta around, or we linearize around the current position. So we make I know where I'm currently at, so I only need the system to be linear around that point. So I calculate the change. Now calculating the change is the same thing as calculating the gradient, right? Calculating the gradient is calculating how much things change when you change one of the parameters. And if you do this gradient for all the variables, then this is called calculating the Jacobian approximation. Right, so if you're trying to filter a nonlinear system like a differential drive robot, then you want to calculate the Jacobian of the position with respect to, in this case, it would be the parameters theta dot and the linear velocity VL. Or to make it look more similar, I'll just call it V rotation here. Okay. How come it's not happy now? Oh. Right, so now I would have my current state, which would be X, Y, VL, and V rotational, right? Sorry, XY theta. Oh. Right, so I want to say if we modify VL, then how much is X going to change Y and theta? And that's basically the okay, I need to do it technically. I need to do it for all of them. So the state of the system, yeah, I'll just put it in here. Now includes the current position, the current orientation, and the current linear and rotational velocities. And the same thing we need to do the Jacobian of the measurement measurements, because that may also be non-linear, the mapping from states to sensor measurements. Now, this may sound intimidating, but this the Jacobian, we usually only calculate the numerical solution for it, right? Because it's an approximation, and I just need to convert it into a matrix form. So I need to have those numbers. And nowadays, that runs fast enough to do that in real time for many applications. So that is sort of an extra step. One interesting extension to so for this Jacobian, let me just more stuff here. So this is the partial derivative of measurements changes due to state changes. Or with respect to state. So this says how much will the measurement change, how much will the state change if, how much will the measurements change if the state changes of the system? Or did I not get the title changed? Yeah, okay. So now you may have also heard of unscented filters, unscented Kalman filters.
Wait.
So this is an idea that is also quite interesting, and often they have better performance as extended Kalman filters, and that you can prove both in theory and in practice. We just have a sip here.
喂，你好，请问是对，嘿，你好，对。
Okay. Let me just mute you. So for unscented Kalman filters, we assume that because of the central limit theorem, that the resulting distribution of our measurements again will be Gaussian, right? And extended Kalman filters map a single point to a through a linearization. Which is an approximation basically from the state space to measurements. And then in the next step for a Kalman filter, then we calculate the parameters of the Gaussian from information that is passed through the linearization. So since we have the Jacobian matrix, we can pass our changes to the measurements due to changes in the state. Then we use that matrix in order to update our estimates of what the Gaussian parameters are. Now, the parameters for the Gaussian, to remind you, that would be the mean and the variance. Right? Those two values are sufficient to uniquely identify any Gaussian. So unsintered Kalman filters take a more direct approach. And the idea is that if I want to estimate and it's sort of like a Monte Carlo approach, really. It's a little bit similar to Monte Carlo methods. And the idea is that I simply take some points around my current estimate I don't need to do this for the entire state space. It's sufficient to do it for the neighborhood that I'm currently in. And then pass them through my system, my nonlinear system. So now I map them from states into measurements that I should be getting, but this could be any function now. I just need to be able to evaluate that function and then calculate the parameters of the Gaussian in the mapped space, in the measurement space in this case. So this is really quite clever. It sort of avoids, because the step in the Kalman filter, the reason why we need a linear system is because then we can prove that the resulting probability distribution is still going to be Gaussian. Under linear transformation, a Gaussian remains a Gaussian. The mean will change, the variance will change, but it'll still, the shape of the probability distribution will not change. If I have a nonlinear function, then that's not true anymore. But if I assume that at the end I end up with another Gaussian, I could just sample that, right? So I can take a couple of points, calculate the sample mean and the sample variance. And this is very easy to implement then. But computationally, it's more expensive. In order to do this well, you may have to project many, many different points. But you can see that the algorithm is would be quite straightforward, and also theoretically you can prove that for it will lead to better filtering, but computationally it's more expensive. So this ends my lecture slides on Kalman filters. Now, if we go back to our original question, what we were trying to do is we were trying to develop a SLAM algorithm, which means I need to be able to localize my robot in a map. And I think it's sort of, maybe not straightforward, but it's sort of reasonable to think about the map building part, right? That one is a little bit easier because the idea is that if I am localized in my neighborhood, in my domain, and I take some measurements and I see that there's a corner or there's a wall or a door, there's a door at a distance that is 2 meters away and 10 degrees from my robot, then you can sort of see that okay, if I look at my map and there's no door there, then I put in a door. So that's not, that's a sort of simpler step, I think, the actual map building. The harder step is if I get a measurement and I say that there should be a door, then how do I actually know where I am currently at? What's the current position of the robot? And in particular, what makes that problem hard would be domains like this. Let me see where my particle filter slides are. So I don't really want to start getting too deep into particle filters here. I just want to discuss one other approach. But I think I want to copy the drawing code that I wrote for here. Who am I? How come I don't have any? Okay, let me try and use a normal paint program. I don't know why Draw refuses to paint now for me. But I can probably draw it on here and then take a screenshot. Let's say I have what? They have this kind of domain. Let me share the window. Can you see the painting now?
Yeah, we can see.
Not really a painting yet, just a single line. So let's say we have a very simple one-dimensional domain, and I have environment where I have a door, right? And now my robot starts driving from the left to the right, and it's currently here. So now when it has a range of sensors, let's say the range of sensors is like this, and I put the robot actually here. Okay. It's a wheeled robot with antennas. Now, if this robot starts towards the right, then what would happen to the estimate of the position and the uncertainty in this estimate? So we start here. Now would be the estimate of the position for the robot. So this here will be my position, right? And this here will be time. Actually, let me draw it the other way around. Maybe a little bit easier. So this is time, and here's the position. So initially the robot thinks it's about here, right? Because the door is like halfway in the center and we're a little bit off to the left. So it thinks it's here. Its uncertainty over time would be some Gaussian distribution with a relatively small spread. Yeah, this one I have to draw like that. So initially we have some uncertainty about the position that we're at. So now the robot moves to the right. So let's say our next position we're here. So now the robot can sense the door, right? And it will start now getting a better estimate for its position. So its position based on the motion. We use a common filter. We would estimate that our position sort of moves, let's say in a straight line. Right? What will happen to our uncertainty? We have an initial uncertainty. Let me put it here. Now we get sensor measurements. So this uncertainty is going to decrease. And the more measurements I get that correspond to the position of my robot, the more the uncertainty is going to decrease. Eventually it's going to increase. Why? eventually the robot is going to be over here. And now there's no more door that it can measure. So there's no measurements that it will get in order to improve its position. So now we're simply doing motion prediction steps, which means that every time we take a step, our uncertainty is going to increase by a constant addition. Right? So, that point. The point where our uncertainty starts increasing is the edge of our measurement space. So in this area range, at these times, we can actually get measurements from the door. So this box is the same as this box here. Right? So this is what happens with a Kalman filter. And of course, if now there's another door here, then things will work okay, because the robot is going to then be able to, or maybe not a door, but there's a table or a chair here. So then we get to there. Once we reach the chair, our position estimate is going to increase or maybe correct it a little bit, and our uncertainty is going to decrease again because we can take measurements. So that's the way it's supposed to work. That's the way that we would like it to work. And then everything will be fine. In practice, however, often we have a domain where it's not quite so simple. Let's say we have a domain like this. Just as described before, but now instead of two doors, one door, we have two doors. And my robot stays in the middle at the beginning. And then it approaches. It stays in the beginning at the initial time, and then the next time it detects that it's in front of the door. So what's the problem now?
Yeah, we cannot distinguish from two doors which one is 1 and 2.
Yeah. So what should our uncertainty now look like for this location? If I now measure door. So here my sensor says there's a door.
Oh, maybe eventually you will finding a door between one and the two, a single door.
Yeah, maybe, but what the belief now should be like for this position should be that either I'm in front of door 2, right?
Mm.
Or I'm in front of door 1. And the problem is this is a multimodal distribution. The Kalman filter would then try and approximate this belief with so hard to see. With some Gaussian which has a very wide spread and sort of would look like this. So the Gaussian would tell us that we're right in the middle between the doors, which is not correct, right? That's clearly wrong.
Mm.
So this is the problem by if we use for our localization just the Kalman filter, many domains, the posterior distribution is not unimodal. It must be multimodal because we don't know what position, what part, or we don't know how to rule out one hypothesis from another. So let me just put that in the edge thing. So how can we solve this problem then? Now, if the robot drives to the right, keeps driving to the right, for example, then we could recover, right? Because if we're in front of door 2 and we drive to the right and we measure another door, then we should have started at door 2. But if we start at door 1 and we measure, then we shouldn't measure another door. So if I keep sort of track of these hypotheses, then I could distinguish whether I was in front of door 2 or whether I was in front of door 1. But if I'm driving from left to right, once I measure a door, I don't know which one of those it is. Now, the Kalman filter only allows me to maintain a single hypothesis, which would give me the average of the two positions of the doors, which is really useless. So in many domains, we must keep track of multiple hypotheses. So Kalman filter only tracks a single hypothesis. but many times during navigation, we have to keep, and I guess that's a secret. We have to keep track of multiple hypotheses. That's one way to think about it. The another way would be to have a single hypothesis but then that must be multimodal. Which means it's definitely not a Gaussian. Right? Those are the two approaches. When you think about it, those are the two approaches that we have in order to keep track of this situation. Either I have the black line here and let me switch again. Looking at my drawing here. Either we're following the black line that models that we could be either in front of door 2 or in front of door 1. So this would be door 2. This would be we're in front of door 1. This would be our Kalman filter, which would try and track this with a single hypothesis. Or I'm able to keep track. What I really want to do is keep track of multiple hypotheses. What I want to be able to do is have a probability distribution which allows multiple peaks. So this would be a multi-modal distribution. Or if I can't do that, then maybe the next best thing I could do is
use the multi-model all the time.
Okay, but we don't really have an algorithm yet for multimodal. We'll discuss one soon, but at the moment we don't really know how to do that, right? But there are algorithms, you're right, so that would be possible. But at the moment the only choice we have would be to sort of have two beliefs, H2 and H1, and then to say that my position estimate is either H1 or
H2.
Or H2, yes. right? To have some sort of hypothesis like this. And that's called a multi-hypothesis approach then. Now, we won't go into the technical details of how to do it. It's actually not that hard. Once you think about it, you simply run multiple Kalman filters, right? Which map to the different interpretations of your model. But what's the trickiest part of a multi-hypothesis approach?
We need to know in previous that how many model how many model we need in our system.
Exactly. So that will be the simplest approach, right? The tricky part is, how do I know 2 is enough? How come I don't need to keep track of 4 hypotheses or 8 hypotheses or 1,000 hypotheses, right? So, of course, the problem is if 2 are enough and I calculate 1,000, then I will waste a lot of computation. So, for more complex domains, where until further information, multiple possible positions exist. In that case, our single hypothesis the probability distribution will be multimodal. So that's not a Gaussian distribution anymore. And one approach, track multiple hypotheses. And these hypotheses are unimodal. And then let me see if I can do it this way. Right, so this is the drawing that I had. So one approach for this particular domain would be to always keep track of 2 hypotheses, H1 or H2. Now what will happen as the robot drives around? Well, one of them will have me centered at door 2. One of them will have me centered at door 1, right? If I now keep driving to the right, then either I'm going to detect the door or I'm not going to detect the door. if I detect a door, then the hypothesis that matches door 2, the uncertainty would remain low because I expect there to be a door and my sensor tells me that there's a door. So then the uncertainty is going to be reduced, right? For the other hypothesis, it gets measurements for a door, but according to the map, there shouldn't be a door, so the uncertainty is going to increase. And eventually, one of the hypotheses will simply dominate, which means its uncertainty, the variance, is going to be very small, and the other one, the variance, is going to be very high. Then you can say, okay, at this point, I know I can ignore H2. I now know that I'm at position H1. Initially, they both have the same variance, the same uncertainty measurement, but over time, one of them is going to dominate, the one that actually matches our current position. So then you can say, okay, so this algorithm is called multi-hypothesis tracking. And it was a popular algorithm at the beginning, but the management of the hypotheses becomes problematic. So do you have a static number of hypotheses or a changing number, a dynamic number of hypotheses, right? That would be the first problem. Do you always track 10? Is 10 enough? Do you need 12? If you need 12 and you're tracking 10, then you're in trouble, right? Your system is going to fail. If you track 1,000 and you need 2, then you do a lot of extra work. So then you say, okay, well, actually tracking a static number is let's say static number, so always n. That's clearly problematic. Either I'm missing out or I calculate too much. Dynamic number of hypotheses, then when to add, when to remove them, and when to add new hypotheses. And basically, the particle filter algorithm is to sort of a way to do this dynamic tracking of hypotheses in a very efficient and a very easy to implement and fast algorithm. So it's the algorithm for tracking of multiple of multimodal hypotheses. It does that by having individual particles. Let me just copy that, make it a bit smaller. And we'll look into details for particle filters next class. So that's what we have here then. But multiple hypothesis tracking, especially if you sort of know about the environment, and you can get away with a static number of hypotheses. So if you know that you'll never need more than 10, then that's also a very efficient algorithm. But many domains you really don't know, so you need to support the dynamic number of models, dynamic number of hypotheses, and then the tracking of those becomes difficult. Then you're much better off to just use the particle filter algorithm, which is a very nice framework of basically tracking these multiple hypotheses. Okay, good. Then that's it for today's class. Remember, the assignment is due. And next week we will start particle filters.
Okay. So see you, Professor.
Yeah, bye-bye.
Bye-bye.
So let me try and make that clear visually.